All right, everybody. Oops. All right, is this better? Can someone say it in the chat if this is better? I'm hoping. Awesome, perfect. Okay, hi everybody, welcome back to office hours. So we actually have a lot to do today, so we're just gonna kind of go as fast as we can to try and finish all the chapter 7 material. So what you'll see today is that all the reactions we're gonna go over are pretty much an extension of what we already saw in chapter 6. So that's good and bad. It's good in the sense that there's not so much more learning in this chapter. It's bad in the sense that it's easy to get things confused. So you need to definitely have the alkenes versus alkynes separated, even though they're quite similar. So our plan is basically to cover all of chapter 7 today, and then on Wednesday, we're gonna just do a whole synthesis day. So I'm sure you guys have started prepping for synthesis for your test on Friday, so you guys kind of start to see what I meant by that. And Friday, we're just going to talk about like multiple like common routes that are typically seen with alkenes and alkynes in these synthesis things. So, all right, so let's start with this warm-up. So this is a critical thinking question with vitamin E. And we don't need to read the stuff up top. It's just kind of describing what vitamin E does and how it's synthesized. But for part A, it says, draw the intermediate formed in this reaction directly upon reaction with an acid catalyst H+. So we're really just looking at this generic scheme down here. So it's nothing new. This is really just like a predict the product question. So if I'm rationalizing, regioselectivity wise, where this proton is going to add, on this carbon-carbon double bond, where you're going to say that that proton goes to the less substituted side. Okay, so maybe this side is I guess a secondary carbon, and then this side is tertiary carbon. So the less substituted side would definitely be the secondary side. So that means that this pi bond is going to grab that proton and form a carbocation where that tertiary position was. That's just the regioselectivity rule. So I'll draw down here for part A. Part A should look like this. And I'll just draw the hydrogen so you guys saw where that went. Okay, so that is literally it for part A. Just draw the intermediate that resulted from adding a catalyst. B, from that intermediate you drew in part A, draw the mechanism using curved arrows for the formation of the cyclic ether. Okay, so this is weird. I've never really talked about cyclic ethers before, but this kind of resembles acid catalyzed hydration. Okay, remember, like, it's water plus acid. Okay, so this is kind of the hydroxyl group of water. We already talked about acid, and if you look at your product, this literally is a dead giveaway. It shows, some sort of, nucleophile, which would clearly be my oxygen here with this set of lone pairs, forming a new bond to some sort of deficiency. Okay, well, I have this lone pair, this source of electrons, this deficiency. Although it's not something I necessarily have seen before, I can definitely rationalize how that forms. So, maybe to prove this to you, I can number the members of the ring. Okay, so then that would form. Oh, does it just say draw the mechanistic arrows? Oh, I don't even need to draw the product. It says you do not need to draw the product. So literally for part B, it would just be that one arrow. That's easy. Okay, so that's part B. I'll put that right there. And then for C, draw, what page is on? It's 86, Tatiana, 86. Draw the structure of the possible minor product of this reaction. Okay, so clearly the major product is going to follow Markovnikov's rule, but the minor product is not going to follow Markovnikov's rule. So this regioselectivity choice, we followed Markovnikov's rule by putting this, carbocation on the tertiary position. But we could have also put it on the secondary position. So let's kind of draw that. So if I were to put this on the secondary position, okay. So this would be my, secondary position. And if I were to form that, we would want to draw the possible minor product of this reaction. Okay, so that's just simply, this lone pair attacking that position. So instead of it being a 6-membered ring, it's a 1, 2, 3, 4, 5-membered ring. So if it's 1, 2, 3, 1, 2, 3, 4, 5. I have an extra bond here. I shouldn't have done that. It should go here across cross that out. So 1, 2, 3, 4, 5. On 5, I have this group, it looks like, and put R here, and I scribbled this out. And this is my minor product. So instead of it being a 6-membered ring like we saw up here, it's a 5-membered ring that we saw down there. All right, and that's it. It's so, yes, this looks crazy, like a really complicated application question, but not too bad. Okay. Any questions on this? I think so. Great. Okay, so we're going to move on to one more critical thinking. It's page 87. So this is with stronglin. So stronglin is this like natural product used, I guess, or made by these like bacteria or something like that, if I remember correctly, some sea slug, I think it is. And they make these products or whatever. So provide the structure of intermediate A. Okay, so it looks like we have this kind of, let's see, we have a question. Marcy, why would you not rearrange the C cation to be a benzylic? Okay, so the question, correct, you could have done a carbocation rearrangement. However, the bigger driving force in this reaction is the ring closing. Okay, so, you know, this formation of this ring is a very stable product. For reasons we don't necessarily know now, it's an orgo-2 thing with conjugation. How else can I explain this? Also, if you were to rearrange to, you know, this 4th carbon right here, the closing would be a 4-membered ring, and that has too much of this like significant ring strain to form that product. You don't want to form a 4-membered ring. So leaving it at this 5th membered or this 5th position, you know, the secondary part, that's how you're going to close it. So David, I think you're definitely right in the sense of like you see a potential rearrangement, but this question was asking like, draw the minor product, and that minor product was like just the other one from the other carbocation, if that makes sense. Okay. Let's go back to stronglin. So clearly we're going to do 2 sorts of rearrangements here. It says 2 successive carbocation rearrangements. So provide the structure of intermediate A. So it looks like you're shifting from here to here. So looks like the first one is going to be that exact same structure that I saw. Okay. However, it looks like I can move a hydride from this original structure over to the right, and that moves my carbocation to a new tertiary position. Okay. So that is providing the structure of intermediate A. And I'm gonna, if you guys are having some like thoughts in your head of why am I even rearranging, I'll explain that in a second. So provide the structure of intermediate A. Then B, draw the mechanism for rearrangement of 1. Okay, well, that would just be that. Okay, done. And then C, what type of rearrangement is rearrangement 1? Okay, well, rearrangement 1 was a hydride shift. Okay, and what is rearrangement 2? Rearrangement 2 looks like we moved this alkyl group over towards the right. Okay, so that would have been an alkyl shift. Okay, and that is literally this question. So it's a different way it looks applied, you know, and it is applied, but you guys definitely have the ability to answer these questions. We're not going to give you anything too crazy. If you guys are asking, you know, we said when you do successive rearrangements, each step has to be, you know, more and more stable. So maybe you're asking, why am I going from a tertiary to another tertiary to another tertiary? And this is catalyzed by enzymes. Okay, so naturally, if we didn't have enzymes, this would not happen. But in regular everyday systems, we can, in regular everyday systems, you can do successive, you know, rearrangements if each one is more stable. But with enzymes present, you can bypass these with like these different energetic things that are going on. Okay, so stronglin and this bio application, we're able to do these. Okay, any questions on that? All right. So we're going to go into the chapter 7 reactions. So if you're following along, we're going to be on page 75. I'm skipping alkyne nomenclature. You guys see it's like literally the same exact thing as alkenes, just "ine" at the end. So, and I think I have a YouTube video on that, so you guys can watch that too. Okay, so the first thing, this is the most important reaction for your test. Like I really promise you guys that. You need to know acetylide substitution like back of your hand. Okay, so what it is we have this, you know, reagent that we haven't seen before. It's called sodium amide, okay? And we have this solvent. This solvent is ammonia, okay? The solvent isn't going to do anything. But for our purposes, we can really just think about what sodium amide is going to do. Okay, so what sodium amide is going to do is it's 2 separate components. It's ionic, so it's sodium positive cation, and then NH2, you know, anion. Okay, so that NH2 looks like an amino group, and amino groups we know are bases. Like these are very basic species. Whenever you see nitrogen, it's typically a base. So what is so special about this, you know, structure? Well, we said back to acid-base chemistry that the more S character something had, meaning, remember when we were talking about, let me go on a section paper. We were talking about, you know, sp3s, sp2s, and sps. And if we're talking about percent S character, percent S, there's one S out of 4 total orbitals, so that's 25%. There's one S out of 3 total orbitals, that's 33%. And then there's one S out of 2 total orbitals, so that's 50%. So what is the, you know, hybridization of this, you know, triple bond? It's definitely sp. So that means I have a lot of S character. And what do we say about S character? Well, as it increases, you have your increasing electronegativity. Well, if we have, you know, like that same structure of a pi bond, and we drew that kind of field of electron density that I drew back in acid-base chemistry, you can kind of rationalize what this proton is. And this proton is acidic, if you guys can now rationalize that. Because of how electronegative this triple bond is, it makes the terminal proton extremely, extremely acidic, or extremely incapable of being deprotonated. Okay, so we're going to remove these protons, form an anion, and then that anion is going to attack something else and extend the carbon chain. All right. So basically what I mean here, the role of sodium amide is to be a base to deprotonate that acidic proton. So let's draw, you know, that mechanistic step would be that into that. So the result of step 1 would be a structure that looks like this. Okay, so that would be step 1. And this is called the acetylide anion, acetylide anion. And this anion can actually attack alkyl halide. So alkyl halide is just a fancy name for haloalkane. So we've seen those before. That would be like, you know, all carbons and hydrogens and then a halide. And it can attack an alkyl halide to extend the carbon chain. So what is step 2? So step 2 shows me it looks like propyl bromide. So 3 carbons and a bromine. So let's draw that. 1, 2, 3, and a bromine. Okay. Let's kind of rationalize our dipole moment again. Maybe I don't really know how this is going to react, but we know that towards the bromine, it's partially negative. Towards this carbon, it's partially positive. So it looks like a nucleophile with an electrophilic carbon. So my mechanistic arrow should definitely be source to sink. And since I exceed the octet, I have to break. Okay, so that would be my next mechanistic arrows. And now it looks like I'm adding 1, 2, 3 carbons in addition to that. So let's draw that structure. So this would be 1, 2, 3 carbons. So that's my structure. And that's it. So notice how we went from a 1, 2, 3, 4 carbon starting material to a 1, 2, 3, 4, 5, 6, 7 carbon starting material. So 4 plus 1, 2, 3 carbons makes a 7 carbon product. Okay? So this is extremely, extremely important. And this is going to be guaranteed to be a step in your synthesis on the test. I can guarantee it. Okay? So anybody have any questions with this acetylide substitution reaction so far? And then we'll just get quicker and do some more. Okay, so let's do it again. So we know what the role of sodium amide, it's going to deprotonate that terminal proton. Okay, so that goes away. We have this, you know, anion, and then that anion can attack this structure, you know, break off that bromide, and now we have a structure that looks like this. So we have a new carbon bond, and then we have, so it's that one extra carbon, this one extra carbon, and the benzene ring. So that's it. Okay, always number, because you don't want to like lose carbons. That's a very common mistake, is that people kind of drop a carbon, add an extra carbon in their product. And I think for you guys, you're just gonna have to be able to identify it. Obviously it's multiple choice or something like that. So for your purposes, just make sure you're counting this the carbons on your screen. All right, so that's it for A and B. Any questions before I move on? Great. All right. I'm gonna keep going. So we're gonna do one more. So let's actually do E, because E is a little bit more complicated. So in synthesis, I'm gonna star this one, because this is something you can do in synthesis. Again, we know what step 1 is gonna do. Step 1 is going to deprotonate that terminal proton. Okay, so now we have this anion. That anion is gonna attack this bromide, okay, or attack the carbon that's next to the bromide, facilitate the removal of it. So let's draw the products of step 1 and step 2. So it looks like we're adding 1, 2, 3, 4 carbons. So 1, 2, and then the triple bond is between 3 and 4. So 3, 4. So let's just double check that. So we should now have on that substituent 1 carbons, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6. Okay, so that would be 1, 2, 3, 4, 5, 6. I'm good. Okay, so then step 3 is going to remove this proton now, okay, and put an anion there. And then it's going to add even 2 more carbons, 1, 2. So let's just do that. So the resulting structure is going to be 1, 2. All right, so now my total structure should have 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. I know how crazy that looks, but you can do multiple additions of this. You know, your alkyl halide, this is where I'm talking about synthesis. Your alkyl halide that you choose to react can have a triple bond in it, and then you can do another reaction of it. That's why I would definitely know this. This is a good idea for you guys, okay? And that's it. Any questions on acetylide, you know, addition? Before we move on to the next one. Great. All right, so if we have these, this is a structure called a vicinal halide. Vicinal just means adjacent. You see that up here. Vicinal just means adjacent. So we have these halides on adjacent carbons. So we see now instead of one equivalent, which means just like 1 mole. So equivalence just means stoichiometric ratio. So I have 1 mole of this starting material and I have 1 mole of this reagent. So it's going to be complete 100% reaction. Here, 1 mole of starting material, but 2 moles of reagent. And that's weird. Why do I have more of my reagent than I would have of my starting material? And let's kind of rationalize that. So I have these protons on these vicinal, you know, carbons as well as those halides, and I'm going to do my first equivalent. So let me just assume I'm doing my first equivalent. So essentially what happens is I have this amide anion or amino anion, and it's going to deprotonate a proton. Let me just pick this one. That electron density is going to be donated into the linear alkane to form a double bond, and it exceeds the octet at this adjacent carbon, so that fluorine has to leave. So it's actually kind of this concerted 3-arrow, you know, mechanism. So that's just the result of our first equivalent. So what's the resulting structure of that? Well, that looks like now this. So from one equivalent of amino anion, we're able to form an alkene. Okay, so what do we think the second equivalent's going to do? Well, it's going to do the exact same reaction. Okay. So it's going to grab this proton, donate the electron density into the linear alkane, and then facilitate the removal of that fluoride. So now we formed a triple bond. So it should be 1. So remember, the triple bond is going to be between 2 and 3. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So that is my structure. 4, 5. Okay. So you can see if we're given maybe this starting material, I can, you know, do 2 equivalents of sodium amide and, you know, ammonia to get an alkyne, I'm sorry. And if this alkyne was terminal, like at the end, I could have done an acetylide substitution reaction, extend the carbon chain, and keep going from there. So you can see how we can do some of these reactions in series, you know, to form a really cool product. All right. Why is a halogen always present in these 2 reactions? Okay, Taylor, great question. So halogens are present because it's something called a good leaving group. You're going to talk about that in chapter 9, so you're for exam 4. But because fluorides are, you know, really, really electronegative and close to that octet, you know, noble gas configuration, I guess you could say, it's really easy for them to leave a molecule. And that's why we see halogens with this reaction, because they're really capable of leaving your molecule easy. Basically meaning it reacts the fastest or the most efficient, if that helps you. Okay, yeah. All right, so let's do G. So for G, we have 3 equivalents of sodium amide, and we haven't seen 3 equivalents before, so I'm wondering what that's gonna do. Okay, so essentially, let's just do the same thing again. So we have this amino group. I'm gonna draw these hydrogens in, grabs a proton, donates into the ring, kicks the bromine off. I'm gonna do it again for the other guy. Grabs a proton, donates into the ring, kicks it off. So that's 2 equivalents. So let me draw what the resulting structure of 2 equivalents would look like. Oops, I probably didn't draw that right. It's gonna be, and it's gonna be between, let me see, here we go, 1, 2. Just make sure I got my carbons right. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, again, always count. You can see how I even keep doing it. It's really important. So this is the result of 2 equivalents of it. So that third equivalent is going to remove this proton, okay? And then step 2 is just water. Well, water, I don't really know how it's going to react with an alkyne yet. We haven't talked about that. All you can rationalize is water is a proton source. Remember, water is amphoteric. It's an acid and a base. So all it does, it's kind of redundant. It just puts the proton right back on. So something really weird, and I honestly never understood it when I was back in Orca 1. I was like, why do we even do 3 equivalents? Why can't we just do 2 equivalents and then be done with it? Because the 2 equivalents, we were already at that structure. But for some reason, when it's terminal like this, you use 3 equivalents to deprotonate it, and then you just have to remember to put it right back on. I don't really know why. I wish I had a better answer for you. Just know that when it's terminal, meaning it's at the end of a molecule, you'll see 3 equivalents and then some sort of proton workup step. But if it's internally in the molecule, it's going to be 2 equivalents. So you can kind of see in H that same thing. It's 3 equivalents again. You know, for I over at the next page, it's again 3 equivalents because it's at the end. Just something to be cognizant about, especially when you're doing synthesis and, you know, picking the answer choice that has the right equivalent in parentheses. So just make sure if it's on the end, it's 3. If it's in the inside, it's 2. All right. So again, you can kind of rationalize the same thing. So we're going to form a 1, 2, 3, 4, 5 carbon acetylide anion. So let me draw that. So a 5 carbon acetylide. So 1, 2, 3, 4, 5. So 4, 5. Okay, so 1, 2, 3. Oops, I'll move that up. 1, 2, 3, 4, 5. So this is where my anion would have been. And then I'm adding this 1 carbon and then the benzene ring. So 1 carbon and then benzene ring, right? And that's it. So I think you guys are kind of seeing the really easy trick here. It's just like, if you see these equivalents, you know you're going to form an acetylide alkyne, okay, anion, and then that anion is going to add into this, carbon structure in 2 to, make this new structure. Okay. Any questions on these? All right. So we're going to move on to I. So here, again, same thing. So you can tell we're going to form this like acetylide anion, terminally, and we're going to add 2 more carbons. So let me kind of draw that. So it's going to be 1, 2, 3, 4, 5 carbon structure. So 1, 2, 3, 4, 5. Okay. And then you're adding 2 carbons. So this should now be 7. 1, 2, 3, 4, 5, 6, 7. So that's the result of step 1 and step 2. Okay, and then step 3 and 4, ozonolysis, it looks like. So DMS is dimethyl sulfide. So remember, it's dimethyl sulfide, aka that. And we know what that is. Okay, so that cleaves these bonds and it forms carbonyls. So it looks like I'm going to form maybe, this is formaldehyde. And it looks like I'm also going to form an aldehyde on the main parent chain. Okay, and those are my 2 structures. So you can see we can bring in alkene reactions to keep playing and keep manipulating all these structures. All right. Any other questions on this? All right. Let's move on to halogenation of alkynes. So this is gonna help you guys in the sense of reaffirming those alkene reactions. So I even said it right here. Alkynes, just like alkenes, are going to react under the same halogenation conditions that we saw in section 6.4. So the equivalence is going to matter here. So one equivalent of the halogen, which we say up here, is going to form this vicinal halide. So that means adjacent. But when you have 2 equivalents, you're going to form this tetra substituted halide. So let me show you what that means. So essentially, you can imagine that we're going to do that same concerted mechanism. So we're going to have some sort of nucleophilic pi bond, grab this bromide, break that. You have some sort of partial character develop on that starting material, which has a lone pair come back. So let's kind of draw what that structure is going to look like. It's a 1, 2, looks like 3, 4, 5 parent chain. So 1, 2, 3, 4, 5 carbon parent chain. The pi bond was between 3 and 4. And it looks like we probably have this bromine bridge. So something that looks like that. Okay. And then bromine is going to come in and attack, bromide anion, is going to come in and attack at, the more substituted position, but it looks like both of them are secondary carbons, so it doesn't really matter which side I pick. In addition, the stereochemistry won't matter here, and I'll explain that in a second. So it looks like we have a bromide here and a bromide here. Okay, clearly the stereochemistry doesn't matter because we're this planar sp2 structure where, you don't have a chiral center. Chiral centers are sp3. So, luckily we don't have to deal with any sort of that, any anti-addition, stereochemical considerations here. Okay. Any questions on that? Pretty easy. We already saw this. And I'll do L again. So, we have that same concerted mechanism, nucleophilic pi bond, comes back, that breaks. So we're going to form this 1, 2, 3, 4, 5, 6 starting material. So 1, 2, 3, 4, 5, 6 starting material. So we have that terbutyl group. We have a 1, 2, between 3 and 4 is our pi bond, 1, 2, 3, 4. So here, looks like this was my main intermediate. So you might be asked to, identify this intermediate. So this is also important. You have chloride, come in maybe, breaks that bridge, and then you're left with that vicinal halide. So, okay, and that's that. Pretty easy. But that was one equivalent. So notice how in this case we have two equivalents. So the same thing is going to happen again. So chloride, chloride. So that intermediate structure is going to look like look how crazy that looks. And then that free chloride is going to come in, attack it. Again, I'm not showing any stereochemical considerations. Why? Not because I'm lazy, but because I know that these are going to be achiral centers since we don't have four separate substituents or four different substituents on these carbons. Okay, so we actually don't have to consider stereochemistry for one equivalent or two equivalents. So it's kind of nice. All right, so that's L. I'm trying to see if there's anything else worth doing. Okay, yes, let's do N. So I'm going to skip M because M is the, so M instead of, the only difference here is that instead of it being, two equivalents of the same thing, it's going to be one equivalent of bromide and one equivalent of chloride. So the resulting structure would be, a bromide and a chloride and a bromide and a chloride instead of, all chlorides. That's it. Okay, so let's do N. N is important. So, bromine with DCM is going to do, the halogenation conditions. I'm not going to draw stereochemistry for now because it doesn't look like it's going to, I guess, impact my answer. So right now I have this, bromide, that adds via anti-addition. Okay, we can draw those major stereoisomers if we wanted to. And then you can see in step 2, we're going to deprotonate. It looks like we're going to do that dehydrohalogenation reaction. Okay, and there's two equivalents of it. So we're going to form this, internal, I guess, alkyne, internal alkyne. And it's between, carbons 2 and 3. So it looks like it's 5 carbons, right? 1, 2, 3, 4, 1, 2, 3, 4, 5. Yep, so 1, 2, 3, 4, 5. So that would be the result of steps 1 and 2. Okay, so you have this internal alkyne. And then we're just going to do the halogenation condition. So it's excess. So excess means more than two equivalents or just like overwhelmingly high amounts of it, basically. So that means that you're going to react twice, essentially. So what that means is we're going to have, basically a 1, 2, 3, 4, 5 carbon structure. So 1, 2, 3, 4, 5 carbon structure. That triple bond was between 2 and 3. So 2 and 3. And if I have excess, I can just kind of predict that there is going to be as many chlorines as possible on those, carbons of that triple bond. That's the structure. Let's set parentheses. Okay, so that would be for N. All right, so you can see how we can do multiple reactions in series. Okay, so it's important. Oh, okay, so we're gonna do, again, bromination. So we're gonna do, this kind of structure. So we have a bromine there, maybe a bromine here. Okay, so it looks like 3 equivalents. We know what that's going to do. That's going to form a acetylide anion terminal. So it looks like it's going to be a 1, 2 carbon acetylide anion. Okay, so that's step of 2. 3, we're going to add 2 more carbons. So I'm just going to kind of draw over it. So it's 1, 2. Okay, and then bromination of that. And look how it's in 2 equivalents. So we're going to imagine that on carbon 1 and 2 of that substituent, each one of those are going to have 2 bromides. So it's a 1, 2, 3, 4 carbon substituent, 1, 2, 3, 4. And we said that pi bond is on 1 and 2. So that would expect a bromide there, a bromide there, a bromide there, and a bromide there. Okay. And that would be the structure for O. Any questions on that? This is really easy, and the best part is there's really no stereochemistry to consider. All right, let's keep moving. So we have, I think, 3 more reactions to cover. Oh, no, we don't. We got a lot more. All right, so let's just keep pushing. All right, so this is basically hydrohalogenation, but just of alkynes. So we've seen this before. And the stoichiometric quantities, again, do matter, 2 equivalents versus 1. So let's kind of rationalize that. So the first equivalent is going to just, have this nucleophilic pi bond, grab a proton, and we generate iodide. So the result is this kind of 1,2 carbon, double bond now, and that hydrogen goes to the less substituted side, so the primary position of that carbon, to form a carbocation on the more substituted side, okay? And then iodide, free iodide, is just going to come in and attack that position. Okay, so then the result of that is going to be this iodide on the benzylic carbon. Oh, I think I just did too many bonds, my bad. Let me scribble that out. I'll draw it over here. So what it would have been, okay, so that is the result of one equivalent. So I'll write 1 EQ. Okay, let's do it again with the second equivalent. So we have HI, so that pi bond grabs H. Okay, now this might be really confusing to you, and it was for me, honestly, too, at first. So the carbocation actually goes here. And that was confusing to me because I'm like, it's really close to this inductive group, right? Like, it's so electronegative. We talked about the fact that even though this is a more stable carbon position, the fact that there's an inductive group right next door or attached to the same carbon is really bad. But actually, you can't think about this in the sense of induction. You have to think about it in the sense of resonance. And there's actually, even though it's not going to partake in resonance that much, they do have these lone pairs next door that can donate a little bit of electron density to fix, that deficiency. So yeah, at first I was like, whoa, that's weird, there's an inductive group there, but not really. So then that free iodide, again, is just going to come in and attack that position. And then the result is going to be this kind of di-substituted iodide. So the difference is that here, it's not vicinal, meaning it's not adjacent. It's on the same carbon, okay? So geminal, you could say. I think, did I say that up here? Instead of synthesizing di-substituted vicinal alkyl halides, this reaction will form a dihalide, so kind of something like this. Question, Farah, how do you know when to interpret the halogen as induction versus resonance? Okay, if it's directly attached like this, directly attached to that carbocation, it's going to be resonance effect, okay? If it's like, when you see like the ranking the carbocation questions, so like, see maybe like a structure like this and it's so far away, that's an inductive effect because the lone pairs are too far away. Does that make sense? Versus, that, when it's exactly on top of it. Yeah, okay, seems like you got it. Yep, all right. I know, I was like really confused with that too when I was in Orgo 1 as well, and then it took me a while to figure that out. All right, so Q would do the same thing, so I don't think we need to do that one. R, okay, again, instead of, let's just do an example of that. You don't have to show that it's going to be just two equivalents of one material. You can do 1 and 1 as separate steps. So I guess the result of step 1 is going to be a 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 carbon starting chain. And it looks like we're going to have it on the secondary position. So we're going to form so that's the result of the first equivalent. Okay. And then the result of the second equivalent is going to form a carbocation here. And then the chloride is just going to attack right there. So I'm just going to go right to the product. All right, and that's that. Pretty easy. But stereo chemistry to consider here. So that's the one thing that, so I do say that you don't really have to consider stereochemistry, especially with the two equivalents, but this one's a little unique. You can kind of see why I have to deal with that stereochemistry. It's because the bromide and the chloride came in and they're not the same, I guess, atom identity. So you have to consider maybe a wedge dash and potentially the dash wedge. Okay, just make sure you guys are also thinking and you're not just kind of like memorizing, like make sure you can double check and see like, oh, did I generate a Carlo center? Okay. I think that's good for this. Yeah, let's keep moving. All right, so any questions on hydrohalogenation of alkynes? All right, great. Okay, so acid catalyzed hydration and hydroboration oxidation conditions exist for alkynes, okay? They have different reagents. We don't know the mechanism at all. And we don't necessarily know the full picture of what it means to be an enol or a keto tautomer, okay? That enol and keto tautomer stuff comes up in chapter 16 of Orgo 2. So for the purposes of you now in Orgo 1, all you need to know is that the keto is more stable. So right here, keto is more stable. Enols will readily tautomerize to the more stable keto. Okay, and that is all you need to know. Just the keto group, which looks like a ketone, and I'll just draw R and R prime for the rest of the molecule, is different from enol group, okay? Enol, so this is the keto tautomer. This is the enol tautomer. Where does that come from? Well, this looks like a ketone, so that makes sense, keto. And enol comes from alkene, ene, and alcohol, all. So alkene plus alcohol is enol, okay? So ketos and enols. And this is something, these are related. So it's a specific type of isomer. We didn't talk about it in the isomer chapter, but it's called a tautomer. And tautomer, by definition, are structures that differ in the placement of a double bond and a proton. So isomers that differ with placement of pi bond and proton. Okay, so H, you can tell the H from, you know, this enol actually goes here, and that carbonyl, instead of, this carbonyl pi bond actually goes here. So you can tell that it's just interconversion, moving these things in different locations, okay? So these are in, you know, dynamic equilibrium with each other. We're gonna talk more about it when you get to Orgo 2, but for the purposes of right now, this is all you should know, and that this is the preferred one, keto, okay? Great. So what happens here, the first thing you wanna do is you wanna say, around your alkyne, what is my substitution? Here, it's primary carbon. Here, secondary carbon, okay? Well, we talked about acid catalyzed hydration and alkenes being Markovnikov addition, and that's what they are here. So let's go right to the enol tautomer, okay? So let's form basically, let me just, sorry, I'm kind of all over the place. I just wanna go back here and just reaffirm what this was. This is what I mean by acid catalyzed hydration. Okay, so we had hydronium. Pi bond grabs the proton, oxygen retains the electron density. We formed a carbocation on the more substitute position. You know, we had water come in and attack. Okay, boom. And then we had one final deprotonation step. I'm just gonna say minus H plus, so you guys know where I got. So I got basically an alcohol from this pi bond, essentially. And the exact same thing is gonna happen. You are gonna form an alcohol following Markovnikov's rule on the starting material from this, okay? So essentially, let's draw what that looks like. Okay, so you guys can understand that. All I did was, I did the exact same thing I did before. It was taking that unsaturation point, or this pi bond, forming an alcohol. But since there are two unsaturation points, or two pi bonds, one just is left over. Okay, is that okay? Is everybody good with that? This is my enol. And we said that enols readily tautomerize into the more stable keto form. So all you have to do is pick this one. And this is my answer. Okay? Anybody have any questions with that? All right, I know it's a little weird. There's no mechanism. We don't have the full picture yet. Just know that for now. All right. Okay, so has anybody made any sort of big aha moments in the sense of like carbonyls? If anybody can understand what I'm talking about is, we know two reactions now, and only two reactions that form carbonyls. One of them was this one, and the other one is, somebody want to put it in the chat box? How do I form carbonyls in structures? I'll give you guys a second. Somebody wants to say it. Perfect, ozonolysis, exactly. You guys all got it. So that is really, and I'm really gonna level with you guys. Honestly, like, you guys have about, I think, what, 20 reactions for this test, and half of them are kind of like a repeat, but you are so limited right now in the sense of what you can do in your synthesis. Like, if you see a carbonyl in your end product, like that's the goal, you know, like 2 reactions to get there. You know what I mean? You have to mentally think in your head, you're like, I only know 2 ways to get there, so I have to use one of them. Like, you know what I mean? So when you're in Orgo 2 and it's now 160 reactions, yeah, it could be anything. but right now it's good for you guys in the sense that you only know like very few reactions. So like it's gonna be pretty obvious for your first test. All right, let's keep going. V, all right. So again, first thing I do is classify. Okay, so I see I have a secondary carbon, I have a secondary carbon. Ooh, what does that mean? That means that I'm gonna have a mixture of products. I'm gonna have two major stereoisomers here because they are both the same substitution in terms of Markovnikov's rule. So let's draw the first one. So let's draw the enol, 1, 2, 3, 4, 5, 6. So it's a 1, 2, 3, 4, 5, 6 carbon chain. On 1, 2, 3, we have a pi bond between 3 and 4. So 1, 2, 3, 4. So here's my ene version of the enol. And I could either have chosen to put the alcohol here, or I could put it on the other side of that pi bond. So maybe here. Okay, and those are both the enols, and these need to tautomerize into the keto form. So keto form is going to look like that. And then this keto form is going to look like, did I miss one? Yep, and here. Okay, so these are not the same structures, you can tell. We have a keto on position 3, and we have keto on position 4. Okay, so it's this one and this one. All right, cool. All right, so for this guy, we have a primary position and we have a secondary position. So clearly we're going to want the secondary position. So it's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And in between 1 and 2 is where my enol is going to be. But specifically, that alcohol is going to be on 2. And then that's going to tautomerize into a keto on position 2. That's it. You can see how easy this is, especially now that there's no mechanism or anything like that. Okay, again, so we have a situation where we have secondary and secondary. So you would have two mixtures of products. So, let's say on the substituent, I'm 1, 2, and 3. So I'm expecting carbonyls on 2 and 3. So look how fast I'm getting at this now. When you see the trends, so this is a 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, boom. And I knew it was between 2 and 3. So 1, 2, and there was another one on 3. Boom. And it's those two structures. Right? And I'm going to leave Y for you guys to do at some point. Okay? So you guys get that? It's pretty easy. And, you might be asked to draw the enol and the keto tautomers like isolated or identify them, in a list of, I guess, structures and multiple choice. I don't really know how that works. But essentially, let me draw the enol tautomer. It's acid catalyzed hydration, which means we're going to, but that's actually worth noting. This underline is underlined on purpose because it's a big hint to tell you Markovnikov. There's also another reaction that's not Markovnikov for this, so that's why that is. So it's 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. We get this ethyl group, and since it's Markovnikov, oh, enol. Oops, sorry, I just drew the keto. I'll just flip it. Okay, these should have flipped. Sorry, I drew them in the wrong boxes. But you can see, maybe we would ask you, draw the keto, draw the enol one, even though you know the keto is stronger. Why is the keto stronger? I'm not going to give you the full picture right now. Just know that a carbon-oxygen double bond is a lot stronger than a carbon-carbon single bond. I said that backwards. A carbon-oxygen double bond is a lot stronger than a carbon-carbon double bond. We'll just go with that for now. All right, and that's enough for now. All right, let's keep moving to hydroboration. So exact same thing that we saw with hydroboration of alkenes. What did that do? That was anti-Markovnikov addition. If it's anti-Markovnikov addition, we're going to add to the less substituted side. And what is this region? It looks like the singer, Sia. And what Sia is, it's an abbreviation for di, meaning 2, sec, S-E-C, iso, like just the prefix, amyl borane. So we're not going to draw what that structure looks like, but what you can do and what you can imagine is it's just like we saw before. There is a sterically hindered side. These are big, bulky groups. Sterics and not sterics, I guess. I don't know. That's what I'm going to say. Not sterics. And we remember what the source of hydroxide was. That's how we formed the alcohol. And peroxide, we didn't really know what it did. And THF, the same thing. So that's what these reagents are. So, a great way to remember it is just think of the singer, Sia, and it's borane again. So it's maybe, I think Sia is great, but if you want to memorize it, it's boring Sia. I don't know. Borane, Sia, I don't know. Maybe that helps you. So what it is it's going to do the exact same reaction, but just do the carbonyl or that keto on the less substituted side. So it's really better to say I'm going to form aldehydes, especially in this structure. You're more likely to form aldehydes with this reaction. So, here we see I'm secondary. Here we see I'm primary. So we want anti-Markovnikov, which is the primary position. So we're at 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Okay, and then on position 6 is going to be that carbonyl, which forms the aldehyde. Okay. For AA, again, we have a combination of two secondary structures. So we're going to get, again, a mixture of products. So this 1, 2, 3, 4, 5, 6 starting material, 1, 2, 3, 4, 5, 6 starting material, is going to have, a carbonyl on position 1, 2, 3, and position 1, 2, 3, 4. So 3 and 4. Again. Okay. The best part is not really much stereochemistry for alkynes, which is pretty good. All right. Again, BB. So we don't have a mixture, we don't have a difference in substitution here. We have secondary and secondary, but there's symmetry, okay? So you would think that there's actually two products, but there's not. You're really gonna form, I could say, two equivalents of the same product, essentially. So one starting material forms two equivalents of products because of the symmetry. Okay, so you can kind of just say that there's one product here. It's a 1, 2, 3, 4, 5, 6, 7, 8. So it's an 8-carbon chain. So 1, 2, 3, 4, 5, 6, 7, 8. And there's no difference in substitution. So 1, 2, 3, 4. So 1, 2, 3, 4. Not. And again, if you can see, if I would have done it from this side, 1, 2, 3, 4, they would have been the same via flipping and rotation. So we only have one structure for this. CC would do the same thing. DD would do the same thing. So I'm not going to do those again. Okay, so then now we can rationalize, 5, which is draw the keto and enol tautomers from hydroboration condition, which tells me anti-Markovnikov. So let's go there. That's where we're almost done, guys. I know I'm giving you a lot, but okay, so the enol tautomer is going to be this 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, carbon chain. And it looks like since it's an enol, it's going to be an alkene at the terminal position. I'll draw that hydrogen just because I want you guys to know that it's at the end, and that's my enol. And if I wanted to convert it into my keto tautomer, which is really aldehyde for this guy, it's this. And you guys can do B and C on your own. You can see C is a little different because C, we don't have a more or less substitute position. So you would get, the same product because of the symmetry. Okay. Anybody have any questions up to this point? We are almost done. We're on the last part, the last reaction now. Can you guys see me okay? Everything's good? I know it cut out for a second. Someone just called me. Do we have to write out the H? Tatiana, which H? Are you talking about this H or this H? Or both, honestly? Or both. Yeah. I have seen it in keys where it hasn't been drawn in, but every semester, like, people are picky on the test. When they're normally on paper, like, graders would normally take points off for that. Your multiple choice. So just for you, draw the protons. Like, for aldehydes, it's part of the functional group. It's at the end. It's like, I've never really seen, like, even on MCAT or like, any of those exams, like, they never just draw an aldehyde without the H. Like, it's weird. Like, you normally have the H there for both of them if they're terminal. All right, 17, catalytic reductions. You're welcome. Okay, catalytic reductions. So we have 3 versions of this. So let me go on a separate sheet of paper, and it's important to keep them in track. Okay, so let's say I have, something like that. Okay, and I'm going to do like a web, so this is more clear to you. 1, 2, 3. Great. Okay, so we know one of these already. So let's just do H2, so hydrogen. So it's our source of reduction agent. Reduction means we're giving it electrons, so we're giving hydrogens to this unsaturation. I kind of proved that with like the fatty acids and stuff. We have platinum, palladium, or nickel. You don't have to write all 3, you just pick one of them. And we said it brought alkenes to alkanes. Well, it does the exact same thing. This is a very strong reducing agent. Let's say strong. And it's going to reduce it again to an alkane. So it's a 1, 2, 3, 4, 5 carbon. 1, 2, 3, 4, 5. So we're literally forming pentane. That's it. We know that. It's one of the reactions. Then there's two other variants of that. So again, they're all involving, so this one's gonna involve H2, but something called Lindlar's catalyst. You do not need to know what Lindlar's catalyst is, just know that that's the name of it, Lindlar's catalyst. And specifically what Lindlar is gonna do is it's gonna make a Z alkene. Oh, here we go again, the Z and the E's, right? The Z alkene. So 1, 2, 3, 4, so it's between 3 and 4. So 1, 2, 3, 4, 5. That's Z, remember? Let me prove why it's Z if you guys forgot. You put a line through this, you talk about priority. 1, 1, 2, 2 in terms of atomic number. Since the highest priorities are on the same base, this is Z, same side, Z. It's German for like, maybe I speak German here. I think it's like Zwaz or something like that, Zwazerman or something, which means same side. I don't know. All right, so that's that. H2 and Lindlar's will form the Z alkene. Remember that. Okay, and I'm going to talk about something after. Wink, wink. Okay, remind me if I forget about that. Okay, and the last one, the last reduction is going to be something different. So it's pure sodium metal. That's what that not means. This like degree symbol just means like pure elemental, like sodium, and dissolved in this like liquid ammonia. And what that's going to do is it's not going to form the Z, it's going to form the E. And that's literally it. So it would basically form, 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5, and it's between 3 and 4. So that's the E guy. E. Okay, so that's just the difference in reduction. So we would classify, these guys on the left as weak. Okay, weak because they're not fully reducing the whole thing. Here, this is strong because it goes all the way to the alkane. That's it, and that is all of your. Oh, I almost forgot. See, I knew I was going to forget. Okay. Where can we go from here? Something so like specific that like it was like the only thing, like it's like the one thing I would always get wrong in Orgo 1 on this test was to do ozonolysis. To do osmium tetroxide reaction, OSO4, I think it's H2O2 and water. That has to happen from this like Z alkene, and you're gonna see that in synthesis. Like when you're doing these synthesis, routes, and you're thinking what happens after the next step, which happens after the next step. If you see a diol, like a 2-carbon alcohol, like, something like that, like a diol, 2 alcohols, you had to have gone in your synthesis through this Z alkene, because remember it's Syn addition. So the only way to get like this Syn stoichiometry, meaning like, that and that, like would be through that. And then maybe sometimes, and that goes away. And then what you could do is eventually rotate back down. So what I mean by this, and I hope I'm not confusing you guys, is like if I saw this as my end product, and let's say, I'm going to use that same starting material. I'm going to draw this backwards. So it would be, you have like all these arrows indicating you have to form that. So maybe this is my synthesis, right? So going from this alkyne to this, structure. How do I do that? Well, I don't really know what to do yet. So let me get to that alkene because I know I can do some sort of alkene alcohol reaction. So, I don't know. Maybe I tried like sodium and pure metal, or maybe I tried like that one and it didn't work out in terms of stereochemistry, because you can tell if I do, what was it? What was I just saying? If I was doing, H2 and Lindlar, it's 1, 2, 3, 4, that one, that goes there. Now you can do OSO4, H2O, H2O2, which forms the Syn diol, because, or dash dash, doesn't matter. And then this was just rotate. And you can see how that wedge would become the dash. Okay? So just specifically this one target synthesis problem, I would always screw up with like the Lindlar or like I would pick sodium and pure ammonia, and that would be wrong because you in order to get the specific stereochemistry of the Syn addition, you need to go through the Z alkene. I don't know. That's all I'm going to say about it, really. Let's do some examples real quick. So H2 and platinum is really strong, and it's capable of, adding to this, and that. So essentially you get 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Done. That's you get no stereochemistry. H2 and Lindlar. Oh, and look, so you can see this FF is what I was just talking about. You have to go through this Lindlar Z alkene and then do osmium tetroxide addition. So basically the result of step 1 is going to be 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So it's Z. You can see that. And then you can do your Syn addition. So I'm going to erase that, put put that, and you also have to consider the dash version as well. Okay, so those two. Okay, so for this one, sodium and pure ammonia, pure sodium and ammonia is going to form that E alkene. So the result of step 1 is going to be 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, ring. Okay, and it's between 1, 2, 3, 4. I think it's here. Okay, and then it looks like 2 and 3 is ozonolysis. So you're going to get, again, 2 equivalents of that same material. Oops, not benzene. And we have, I guess, that. And you don't have to write 2 equivalents, but I'll just say that so you guys know. 2 equivalents. Okay, and the same thing, you know what H2 and nickel does. So it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's that structure. H2 palladium. Okay, a couple of stereochemical things to consider here. You're not touching benzene. This is going to completely go away. This is going to be Syn Addition. Okay, so you actually have 2 major stereoisomers. So I'm going to abbreviate. I'm going to do it like this. 2, 2, 2, 2, 2. 1, 2, 1, 2, and benzene ring. Okay, so it's one of them. And then you also have 1, 2. And I'm just going to do pH for the benzene ring because I ran out of space. But do you see that? It was Syn Addition here. So if the 2 hydrogens add there, it's going to force that methyl group on a wedge. And if both of them add on wedges, then it's going to form that one on a dash. So, you know, we're never touching benzene, at least until Orgo 2. And this one completely goes away because it's strong conditions. And this one we just had to consider stereochemistry. And that was it. All right? So that actually takes us nicely to the end of today. I think we're at 356. Yeah. So let's just basically look at a couple of things real quick. Okay. I'm going to leave you guys to do this roadmap. So this roadmap should be good for you guys. I really recommend you guys knowing this roadmap. This is how it's typically been asked in recent semesters. So that gives you sort of any inclination, know how to do these. Yeah. Okay, let's talk about B. I always like talking about these. So classify the following reactions either stereospecific, regioselective, both, or neither. Okay. Let's see. So for A, so what it is it's still a hydrohalogenation. We grab this proton. We do follow Markovnikov's rule. Remember, we're forming that more stable carbocation, so that's a regioselective thing. But are we stereospecific? Like, was there Syn Addition, anti-addition, you know, bridged intermediates? Like, no. So this is really just a regioselective reaction. Okay, so R only. Okay, so B. So B is going to be, you know, acid catalyzed hydration conditions. We're going to form the more substituted keto group. So that's a regioselective choice. So it's definitely regioselective, but is there any stereochemistry to consider? No. So again, just regioselective. And here, so this is bromination of that alkyne. Yeah, it definitely would be regioselective in the sense that you would attack, you know, the more stable bromide in the mechanism. You know, remember, at the more stable side. And is it stereospecific? Well, yeah, it was stereospecific in the mechanism because we had, remember, those bridged intermediates where we had that anti-addition. Although there's no stereochemistry to consider in the end product, there was still anti-addition. So yeah, it was both regioselective and stereospecific at some point in their mechanism. So I would say both. And that's it. I just like talking about that one. All right. So that should be good for you guys. That should take us through, I guess, yeah, that's the end of chapter 7 material. So this is what this page 84 and 85 is what we're going to focus on for all of Wednesday. And we're going to try and rationalize all of this. And I would just do the remaining predict the product questions before then. Like this is page 88, 89. These would be like a good way to, like, you know, solidify that you know all of your reactions, kind of stimulate test conditions. And that's pretty much it. So I will see you guys on Wednesday. Good luck.